Dear students, today we will see some of the applications of elastic behavior of the materials. So this will be asked for 3 marks, okay, like what we have seen in the previous classes, like Young's modulus, rigidity modulus and bulk modulus. See, mentioning these 3 will also give you 3 marks. Then other than that, the stress strain curve, that will also be asked for 3 marks. So this 3 mark question here, I have mentioned 4 applications, okay. So any of the 3 you can write for the examination. The first application tells you about the metallic part of the machinery, if subjected to stress beyond its elastic limit, will permanently get deformed. So every material has got an elastic limit, okay. We have discussed in the previous class about the elastic limit. So what happens if I subject this material into certain stress beyond the elastic limit? What happens? It will be permanently deformed. So you should know the exact value of the elastic limit of a particular material so that the material can be used for various purposes. So you can see one such example I'll give. If you have a bridge, okay, so somewhere in the bridge it will be mentioned that the load of the vehicle which should pass through the bridge will be of certain value, particular value, okay. That means the vehicle having certain overload is considered for the bridge, the maximum weight the bridge can bear, okay. So that will be decided by the material what we are using for the building of the bridge, okay. So that's the reason why you should know the elastic limit value of particular material. So if a heavy truck passes through a bridge, what happens? The bridge will get collapsed and maybe there is a chance that it is going to get bent like this. Correct, right? Okay, so one such example is about elastic limit. So knowing the proper value of the elastic limit will help you to select the material for the bridging of various constructions. Okay, so various buildings or other things will be constructed on the basis of value of the elastic limit. Next one is about thickness of the metallic rope used in the crane. So all of you must have seen the crane, right? Okay, so crane uses a metallic rope. You can see this one, okay. I'll draw the diagram over here. So this crane will have a metallic rope so that it can lift particular load. Now this rope should have certain value of Young's modulus, or it should have certain elastic limit value so that the weight which it should lift will be decided. Now you can see here the thickness of the metallic rope used in the crane in order to lift a given load is decided from the knowledge of elastic limit of the material of the rope and the factor of safety. Okay, so we should know how much weight this rope can bear. Then only that rope will be used for the particular lifting purpose. Now, what should be the thickness of the rope? We can decide it from this small mathematical idea. Okay, so the area of the rope should be greater than equal to W divided by, this is nothing but yield strength. I mentioned it as like a SY. Okay, so this SY is nothing but yield strength, you know, it is a stress, right? So this SY is nothing but, we'll take this term to this side, it will be W divided by A. We can write like this, okay. Now the value of the area of the thickness, okay, area or the thickness of the rope should be greater than this value. So what I can substitute for W? W is nothing but M into G, or load is nothing but weight, right? Mass into gravity divided by this yield strength, okay. Then we can substitute this value for a particular load. If you want to lift some 1000 kg or some 10,000 kg, okay. So I'll take here 10,000 kg or 10 to the power 4, okay. Then it will be multiplied by G. G value we will take it as 10, okay, divided by this yield strength of particular material. Whatever material we are using, this is nothing but the value for the steel. Then by doing the calculation you can get the value 3.3 into 10 to the power minus 4 meters square. So this is nothing but area. Now you need to understand that to lift a weight of 10,000 kg, you need to have the area of the rope that should be equal to 3.3 into 10 to the power minus 4 meters square. Now what should be the radius of the wire? You can calculate from the simple mathematical equation, that is, as it is a circle, okay, rope, right? So here, what is area? You know the equation, it is pi r square. If you want to calculate r value, what do you need to do? Take the terms to the other side, then take the square root. So area of the wire is calculated over here. By substituting this value and the pi value, you can find out the radius of the wire which is used to lift a weight of 10,000 kg. Now see, this value is almost equal to 1 centimeter. Okay, value is almost equal to 1 centimeter. So you can understand here, if you have a wire of area of cross section 3.3 into 10 to the power minus 4 meter square, you can lift a weight up to 10 to the power 4 kg. But are you using such a simple thin wire for the lifting? No, right? What we are making use in the crane is that such thin wires will be joined together, or it will be wound together to get a thick rope. Okay, so that means if you take a simple rod, okay, of this much radius, it will be a rigid body. Correct, right? You can understand, if you have 1 centimeter, you can measure. If you take such 1 centimeter radius, then what will be the diameter? Obviously it will be double of that, right? That means 2 centimeter. So if you take a wire of diameter 2 centimeter, obviously you are going to have a rigid body. Correct, right? You will have a rod. So rod cannot produce such kind of effect, or the elastic effect will be less there. It will undergo the what is called deformation easily. That's the reason why what we are making use here, thin wires are used. Okay, so many wires will be used to produce same thickness. So if you observe the rope of the crane, you can see that so many wires will be wound to get a metallic wire. So that is in the case of crane, where we need to know the value of elastic limit so that we can lift different weights. The next application is about maximum height of a mountain on the earth. So you must know that the highest mountain on the earth is nothing but the Mount Everest. And you can, if you search on Google, you can get the value that the height of the mountain is approximately equal to 8.9 or approximately 8.5 kilometer high from the sea level. Okay, so how this height is decided, and why Mount Everest cannot have height greater than that of this 8.5 or approximately like what we have 8.9 value? Why it is limited? So that actually calculated from the elastic properties. Okay, now elastic behavior of earth is going to tell you the maximum height the mountain can have. If you consider a mountain over here, okay, it's a rough diagram over here. Now you see that what we need to calculate, the weight or whatever force getting acted, not on here, it should be over here. So if you consider this small part, I can take it over here. So from all the sides, force will be acting on that. Okay, so you have studied about shear modulus, right? So once the force gets acted on this one, what actually happens? The top side is going to get slided. So if you take something or the sponge or something, and when you apply the force like this, what actually happens? Displacement takes to the sideways. Correct, right? Displacement takes to the sideways. So you can see here, for a small part on the bottom of the mountain, when it gets acted upon by large force, that means the weight of the entire mountain, okay, will be acting on over here. Okay, then what happens? The particles over here will get slided to the sideways. That is the reason why you have the shape of the mountain like this. See, when you people draw the diagrams, like when you were in smaller classes, you used to draw the mountains like this, right? Okay. So why do you draw like this? It is like a pyramid shape, right? It is a reason that whenever the force from the upper part gets acted upon on the lower side, particles get slided to the sideways. It actually happens everywhere. Now, the top will have a sharp edge, but it will be like steep to the sideways. If you consider the elastic limit value, that is something around 3 into 10 to the power 8 Newton meter square, we can calculate the approximate value the mountain can have. So we will use the formula over here. You can see here, I'll make use of this formula. It is nothing but the pressure exerted over here, pressure getting acted upon on this point, that can be written as mg divided by A. Okay. Now, if you want to calculate this one, what we do actually, we will substitute the value for m. Okay, m we don't know. Then what we can do here is we can consider it as a cylinder. Okay, we will consider this mountain as a cylinder. Now, the cylinder has got height h. Okay, and it has got density rho. We will take. Okay, you can see here. From this equation we can write, we don't have the value of mass, right? Mass of the mountain we don't have, but what we can do is we can calculate the value of mass from density and volume. Volume we can understand if you consider it as a cylinder. You can write here instead of mass, that is density into volume, and volume is nothing but it is taken to be height into area of cross section, correct, right? Multiplied by G, then it is divided by A. So what you can do here, you can cancel A and A, correct? So we will cancel A and A. Then what is remaining over here? Rho H and G. I'll write it as rho G H. So rho G H is nothing but the pressure that is getting acted upon on the particle whatever on the bottom. So we can find it out. Like the pressure whatever getting acted upon will be equal to almost, it will be equal to it should be less than the elastic limit. So why I am saying it is less than the elastic limit, if it is greater than the elastic limit, what happens? The particles will get slided to the sideways. So the pressure value whatever we have here, it should be less than the elastic limit value, that is nothing but 3 into 10 to the power 8. Now substituting the value for rho, G and H. Rho we can calculate, like we are taking an assumption, not the exact value, it is like an approximate value. So this approximate value is compared to the water. So anyway you know that density of water is nothing but 1000. So solid materials are having higher density than that, obviously. Okay. So to do some kind of rearrangement, we will take this value approximately equal to 3000. Okay, so this 3000 density multiplied by G value 10 and it is multiplied by H, which we don't know, and it should be less than 3 into 10 to the power 8. Now taking these value to the other side, okay, doing cancellation that you can do by yourself, you will get H less than 10 to the power 4. So what is this 10 to the power 4? It is nothing but 10 kilometer. Okay, so you need to understand that the maximum height of a mountain possible on the earth is nothing but less than 10 to the power 4. So example of this Mount Everest, whatever I have given, will give you the value approximately equal to 8.9 kilometer. So I think you people have not heard about this one, or those who have heard about this one, Olympus Mons. So this is a mountain which is having height 26 kilometer. So are you getting surprised? Like how you can have a mountain of height 26 kilometers when the maximum value possible on earth is 8.9. Sorry, it is approximately 10, and 8.9 is the maximum. So where does this mountain situated? So it is not on earth, it is on Mars. and you can think about it why you can have the value which is approximately 26 kilometer. So you can get the idea from this equation itself, okay, or here you can understand why this value is approximately 26 kilometers from this equation. Okay, you have to tell me after you see this video why it is like 26 kilometers possible on the Mars. Okay, next one is about the designing of bridges. You can see here the fourth example. The bridges are designed in such a way that they do not bend much or they do not break under the load of heavy traffic, force of strong wind and its own weight. So see here, so diagram is given and I'll be explaining this. If the weight is subjected over here, like a heavy vehicle is moving on a bridge, what happens? There will be a sag in the bridge due to the heavy load. Okay, what happens? The bridge will get sag due to the load, and this value of this sag will depend on all these factors what I have mentioned over here. Okay, so it is nothing but load, it is length of the bridge, breadth of the bridge, depth of the bridge, and this is nothing but Young's modulus value. Okay, now I have mentioned all the terms over here, you can read for yourself. Now if a particular load comes through this one, the bridge is going to get bent. Now this value of sag can be reduced by using a material of higher Young's modulus value, correct, right? If you make use of material having little bit higher Young's modulus value, you can reduce the sag, okay, because this term is on the denominator. Similarly, you can look here, breadth, it is just the power of 1. So increasing the breadth will not help you much for the reduction of sag. But you see here, depth is of the power of 3. Okay, it is proportional to, like say you can write sag is proportional to d to the power minus 3. Correct? If you increase this one 3 times, it will be reduced. If you increase this one by once, it will be reduced by 3 times. Correct, right? Now that's a reason why you people must have observed that the bridges are having a thick base, like the depth of the material whatever we are using here will be having higher depth. So increasing the value of depth of the bridge can reduce the sag. Okay, that is the idea. So this values, all these values, like the mathematical idea should be known properly for the building of particular bridge. So each bridge will have different specifications, like it will be used for like a heavy load transportation or light vehicle transportation. So all these values should be properly known while designing the bridge. Now we will go with the pillar of the bridge. See, I told you here increasing the depth can decrease the value of sag, but alone increasing the value of depth will also be danger. That what happens, the bridge will get like it will bend to the sidewise, correct, right? If a huge weight is applied over here, what happens? It is going to get bent. So that you can observe even with a small any material if you take, you can understand that when you apply certain weight, okay, what happens? It bends to the sidewise, right? Howdalva? It bends to the sidewise, so that we need to distribute the weight equally on each part. That is the reason why this type of construction is advised. So whenever you look for the pillars of the bridge, you will see a I shape, correct, right? So what happens over here, in compared to this one, if you increase the material itself, see, instead of having this much thick, okay, so breadth this much, if I make this much breadth, what happens over here? In this case, material needed over here is more, correct? Then you will have higher expense, okay? So increasing the breadth, you know, right, it doesn't contribute much. So only thing, we need depth properly okay, proper depth it should have, then the weight should be distributed properly. That is a main factor. That's the reason why we are making use of this one. Now see, a truck can stand over here, so its weight will be equally distributed and it will be maintained properly. So instead of having, see, weight entirely over here, it will be distributed in this case. Okay, so these are the ideas, and you don't need to explain all these things. You can just mention the applications.